The decision process begins with selecting a whole number n. From this, we create set A containing all whole numbers from n down to 1. The first number n becomes the numerator, and we choose a denominator m, ensuring m is not 0. We divide n by m to get a remainder r1, which is placed in new set B. Next, the subsequent number n minus 1 from set A becomes the numerator. We repeat the division process with the same denominator m, and the remainder R2 is added to set B. This is repeated for each element of A until it's empty and B is filled. Finally, we sum all elements in set B to get the total T. This method ensures a step-by-step logical calculation to solve the problem.
So let's see how we solve this pairwise sum and divide question. First, we consider an array with 3 integers, and we can see that with 3 integers, we could generate 3 unique pairs. For the first case, we consider an array with 4, 3, 2, and in this pair, the integer should be less than the integer j. So likewise, we have generated 3 pairs as shown. So our function is to divide the sum of 2 integers by the product of 2 integers. So using this function, we have obtained the numerator and denominator values for each pairs. And we have to make sure that the denominator is not equal to 0, as it will be undefined if it is 0. So then we have obtained the results after division, and we only consider the integral part of the result, neglecting the decimal part of it. Therefore, for all 3 pairs, we have obtained 0 as in this document. So our total sum is equal to 0 as well. Similarly, we have obtained the sum for the second test case as well. So you can see this in this document as well.
To find the last 2 digits of the big sum like this equation, we use the simple trick called modulo 100. This means we only keep the last 2 digits of each number instead of working with the whole number. For example, if k equal 5 and n equal 3, we'll calculate 1 power to 3, 2 power 3, and 3 power 3, 4 power 3, and 5 power 3, which are 1, 8, 27, 64, and 125. Then we take only the last 2 digits of each result, 1, 8, 27, 64, and 25. Adding these gives 1, 1, 8, 125, and the last 2 digits of 125 are 25. This method is quick and help us work with big sum easily.
Solution to problem number 4. In this problem, I started by defining a sequence using a specific rule. Each new element is the sum of the previous 2 elements, taken modulo m. Beginning with fixed initial values a0 always 0 and a1 equal to a given constant c, I systematically generate a sequence of numbers. Then I transform this sequence into vectors by pairing consecutive elements, skipping the first 2. Using these vectors, I calculated scalar products by multiplying corresponding x and y coordinates and summing the results. The key innovation was my final step. Taking these scalar products, finding their residues modulo m, identifying unique residues, and counting them. In my example, I began with c as 4, modulus as 5, and generated a sequence that ultimately yielded 2 unique residues, just as provided in the output of my problem.
First, you choose a number n. This is the biggest number you use in the calculation. For example, if n equal 5, you work with the numbers 1, 2, 3, 4, and 5. The number n must be between 1 and really large number 10 to the power 16 to be valid. Next, you pick another number k. This tells you how many times multiply each number by itself. For example, if k equal 2, you square the number. If k equal 3, you cube them. The number k must be between 0 and 1000 to be valid. Then you start with the total to t set to 0. For each number from 1 to n, you raise it to the power of k, add it to the total t, and move to the next number. You keep doing this until you gone through all the numbers up to n. At the end, t will be the total sum. For example, if n equal 5 and k equal 2, you calculate 1 square 2 plus 2 square 2 plus 3 square 2 plus 4 square 2 plus 5 square 2, which equals 55. That's the answer.
To solve the problem, we need to first create a series S using the formula Si equal a plus b into I, where I goes from 1 to n. Then we check each number in the series to see if it is a perfect square, a prime number, or a palindrome. We keep track of these counts using prefix sums, which make it quick to answer range queries. For range LR, we can easily find how many perfect squares, primes, or palindromes are in that range. For computation queries, we use the formula which is result equal SP into U plus V times mod m, where SP is the value from the series. This method is efficient and handles all queries quickly.
Circle summation. In the circular arrangement of m children, each children number is updated over m rounds based on the sum of their left and right neighbors' values. Update happened one children at time in a clockwise order. After all round, the final numbers are displayed using modulo 10 to the power 9 plus 9 to keep values manageable. Step-by-step procedure. First one, step up circular structure. Left neighbor I minus 1 plus n mod of n. Right neighbor I plus 1 mod of n. Second one, round updates. Round 1 updates children node. Example A 42735. A node 4 plus 5 plus 2 is equal to 11. A is equal to 11 plus 2 7 3 5. Round 2 update child 1. A1 is equal to 2 plus 11 plus 7 is equal to 20. A is equal to 11 27 3 5. Repeat for m rounds. Handle large numbers. Apply AI mod of 10 to the power 9 plus 7 if necessary. Final output. After m round, output the final array.
This problem involved finding valid matrix configuration under module arithmetic. We initialize a 2 by 2 matrix A where A11 equals 0 and A12, A21, A22 can be either 0 or 1, resulting in 8 configuration. Using guessing elimination module 2, we determine the rank of each matrix. The number of solution is 2 to the power of n minus r, where the n is the number of variable and r is the rank. For example, when A equal open bracket 0, 0 in first row and 0, 0 in second row, close bracket, the rank is 0 given for solution. After the analyzing all 8 configuration, the result of this case is case number 1 to 13. This demonstrates how matrix rank and module arithmetic are used to solve the problem.
At XOR operation, many programming enthusiasts find fascinating the challenge revolves around the calculating the KPRM sum. For a list of numbers based on specific queries, each query is defined by 3 parameters K, P, and R. The task is to be compute the sum of XOR operations between selected elements of list constrained by the indices P and R, further modulated by 10 to the power 9 plus 7 for manageability. To tackle this, the solution involves systematically iterating through the list for every query, computing the pairwise XOR values within the specified range and summing them up. For example, given a list of 1, 2, 3, 4, 5 and queries K, P are K equal to 3, P equal to 2 and R equal to 4, the result is calculated as 11. This problem is not only about computation but also about optimizing nested loops to efficiently handle large inputs. Such problems highlight the beauty of algorithms and how they enable us to solve complex queries with precision and elegance.
My problem, which is rational sums. In this problem, we compute the sum of a series where the terms are in form Pf over Q of n. Q of x is constructed as a product of terms like x plus ai, where ai are distinct non-negative integers, and p of x is a polynomial with integer coefficients. For example, in test case 1, q of x equal to x into x plus 1 and p of x equal to 1. The series simplifies into a telescoping series where intermediate terms cancel out, giving a final sum of s equal to 1. In test 2 case 2, q of x equal to x into x plus 1 into x plus 2 and p of x equal to 1 plus 6. By summing, the result converges to s equal to 7 by 4. The key steps involve constructing p of n and q of n, simplifying the series.